Hello, everybody. My name is Joan Solà, here at the Institute of Robotics in Barcelona. I'm going to present a quick lecture on Lie theory, intended for the roboticist. Lie theory, it's an old and very big theory in mathematics, quite abstract, but for robotics is very useful for rotations, translations, and a lot of geometry operations that we do. And it's a very beautiful framework that allows us to work, especially in 3D, where rotations get kind of tricky, with rigor and precision and so on. We can do derivatives, integrals, estimation, control. We can do a lot of things with this theory. And that's the aim of this course. Lie theory for the roboticist means that from all the material available in this theory, which is very big, it's used in quantum physics, particle physics, and a lot of other disciplines in science, and they use it at the full capacity. We use a very small subset of things from the theory. And the good thing is that through some notations and shortcuts, we can make very nice analogies between the elements of this theory and what we are used to work in vector spaces. So you will see that all the intuitions that we have when working with matrices, vectors, and these kind of things are applicable to what we want to do with 3D rotation matrices and these kind of objects that are nonlinear. And so this is the aim of this course. As a small motivation, I will present a first example of a Lie group, which you all know is the group of complex numbers, so the set of complex numbers, and in particular, the set of complex numbers that have unit norm, okay? And well, you should all know, this is very well known from school, that when you multiply two complex numbers, the angle or the phase of these numbers get added. So if one of the complex numbers is a unit number, and then you rotate the other one, okay? So by multiplying a number x, which is interpreted as a vector in the plane, by a unit complex number z, the result is that we rotated x, okay? So we rotated x, producing y, okay? And we use for this a complex number which is unit length, okay? And this number z is this one here. It has a norm 1 and an angle theta. And the amount by which we rotate x is exactly theta, okay? This is very well known, but we will put these well-known facts into the framework of the Lie theory. So in Lie theory, this operation of rotating a vector through an operator z is called action. This is the action of the operator z on the vector x, okay? To define the elements of the unit complex numbers, we just apply to any complex number a constraint, z conjugate z equal 1. This imposes a unit norm. And you can see that this constraint is a nonlinear constraint, okay? So just by imposing a nonlinear constraint, we will end up with a set which has a certain shape, okay? We call it the topology. And in this case, it's a unit circle. We call it S1, okay? So the shape of this set of unit complex numbers is a unit circle. That's very easy to see. And we call it S1 because it is the sphere of dimension 1. So a sphere, abstract sphere, is the set of points at the same distance from a given point, okay? And this is the surface. And in 1D, so the sphere of 1 dimension, this is a line of 1 dimension. It lives on the plane, but the line itself is 1-dimensional. So we call it S1, okay? The elements of this set S1, we can call them Z, and you all know that they can be written as cosinus theta plus I sinus theta. no big surprise here. And we can also find an inverse of these elements, so that if I multiply the inverse by the element, I obtain the identity. So through the constraint, the inverse of an element times the element is the identity. Okay. And I can also compose different operators like this, so that if I were to apply this number z1, z2 to a vector x, that would mean that I rotate x first z2 and second z1, and I produce a different y. Okay, so I can compose the operations. Okay, no surprise for the complex plane. This is well known, and why not? But all of these keywords, action, constraint, topology, elements, inverse, even the identity element, belong to the theory of the Lie groups. Okay, which is what we're going to explain. There are other examples a little bit more involved than this one. For example, rotations in 3D, unit quaternions, rotations in 2D, of course, rotation matrices, I mean, or even motion matrices, rotation and translation, different kinds of scaling and geometric modifications to shapes. Okay, let's go on. For example, let's use also the rotations in the plane, but using rotation matrices. So you see that I can do almost the same drawing. Okay, instead of 1 and I put the identity matrix here and a weird skew matrix here, and R is a linear combination of these two matrices of norm 1. Okay, R is I cosinus theta plus 1 cross sinus theta, and this gives me cosinus theta minus sinus theta, cosinus theta, which is the rotation matrix in 2D that rotates a vector x here by an angle theta, producing a vector y. Okay, you will realize that this drawing is very much the same as the drawing before. It has the same shape. It does the same things. The vectors x and y now are Cartesian vectors. They are not complex numbers, but who cares? They can be meant to represent the same thing. Okay, and the constraint now is R transpose R equal identity. This shouldn't be a 1. This should be an identity. The topology is a kind of a circle if you admit that the two axes are two matrices, actually. This defines a circle. Why not? The elements, we discussed this already. The inverse is the transpose, and the composition is the matrix product. Here also, you kind of know all of these concepts because they are matrices in 2D, rotation matrices. And the good point of this slide is to show you that everything that we explained for the complex numbers applies here. There's absolutely no difference. If we are able to abstract the details and only retain the concepts, the abstract concepts, we are talking about the same things. Okay? Of course, we can go to 3D and do similar drawings and these kind of things. But for example, let me go back a little bit. Sorry for this. We have elements of different kind. For example, a rotation matrix is a matrix. It's a rotation matrix. And x and y are vectors, in this case in 2D. So the element R and the element x do not belong to the same set. Okay? So the action is performed by elements of this set, which is the Lie group. We will talk a lot about the Lie group, and it's an operator. And it acts, this is an action, it acts on elements of a different set. In this case, it's vectors in the plane. Okay? And in this drawing on the left, I was able to draw all the elements in the same drawing by doing some kind of tricky things, because the matrix R is represented in a base which is I and 1 cross, but the vectors x and y are in the base 1, 0, and 0, 1. So I can draw the things in the same drawing, but I am cheating a little bit here. If I were to use another group, which is the group of unit quaternions, some of you know that unit quaternions may be used to rotate vectors in 3D. Okay. Now I am obliged to separate what happens to the elements of the group, in this case a rotation matrix, and what happens to the elements that are transformed. Okay, I want to separate one thing from the other one, and this course is dedicated to understand what happens or how the Lie group works. Okay, of course it acts on vectors, but remember, the action is just one of the keywords we can apply to Lie theory. It's one of them. There are a lot of other things. Okay, and so we are interested on the left part of this drawing. If we go to quaternions, now I am completely unable to mix these two drawings in the same drawing. There's no possible. That's why it's important to separate the Lie group from the other set and do not mix everything in the same place. If we are talking about unit quaternions, for example, Q is a point in this sphere and its unique length is a unit quaternion, and I cannot draw the two vectors, that the vector that is being rotated in this drawing. It has no place here. There's a different space, and I cannot draw the same elements. Okay. However, a quaternion constructed like this, cosinus theta half plus u sinus theta half, is able to rotate the vector x in 3D, an angle theta, around axis u. Okay, so why not? Very useful, and we use the same principles of Lie theory that we are going to explain. A little bit more. So a little bit more of abstraction. Imagine we have the group of rotations and translations. In this case, in the plane, we call this the special Euclidean group, a special Euclidean group in 2D. Okay, these are elements of this type. R is a 2x2 rotation matrix. P is a 2 vector, and this matrix is a 3x3 matrix. Okay, and each one of these matrices is an element x of t that can vary across time continuously. Okay, so we can draw a point in the group as, for example, here we start at the identity. So R is the identity, P is 0, and we are here. Okay, and this is a kind of a surface, in this case 3-dimensional, that englobes all the constraints of my system. And applying this position and translation to an object in the plane, okay, we are able to produce this kind of things. All right, so we are used to reason here in the plane where things happen. This is everyday life. Okay, there's a plane, there's a robot, and there's a trajectory. Okay, but each point of this trajectory can be expressed as one matrix like this, and each matrix like this is a point in the Lie group space. And so the trajectory of the robot in the real world is the same as the trajectory of a point in this weird space. Okay, so by putting the attention on the left side of this slide, we are already abstracting a number of things. Okay, and so we are able to think mathematically on the left, and on the right we are obliged to think geometrically, which is not exactly the same. Okay, here we will be able to do calculus, algebra, and a lot of things, and here we can just apply intuition and go maybe far, maybe not so far, but usually when you are able to abstract things mathematically, you are able to go much farther in your developments, and that's the interest of having nice theories. Okay, another example. Imagine now we have a set of special Euclidean matrices in 3D, and they represent each one of them the 3D position and orientation of each one of the limbs, for example, of a humanoid robot. And now when you want to make a motion on this robot, you will have a point moving in each one of these surfaces. Okay, this motion here is exactly the same as the motion you see on the left. All right. Okay. So why do we need this? We'll try to convince you now and in the rest of this course that this is important to have. So Lie theory, or the theory of Lie groups, it's abstract, so you can apply it to many different things. It's rigorous, so once you know the axioms and the theorems and how it works, it's rigorous. It's not approximations or, you know, kind of loose things. It's principled, so you can, you know, you have your axioms, you have your conclusions, theorems, and you can do a lot of things. For example, knowing that you have some transformation objects like rotation matrices, unit complex numbers, unit quaternions, you can invert them, you can compose them, you can interpolate between them. That's very nice. You can act on other objects. This is the action that we have seen. We actually started the course talking about the action. For example, rotation is an action. But you can also go to the calculus domain. So you can perform integrals, derivatives. And with these two guys, you can start talking about uncertainty, because you can talk about infinitesimals, small variations of things. So you can start talking about uncertainty, covariances matrices, uncertainty propagation, and these kind of things. And when you are in this kind of, let's say, world of reasoning, now you are able to do estimation, you are able to do planning, you are able to do control, or I'm not a specialist here in learning, but I'm sure you can also do learning in a principled, rigorous, and possibly abstract way. So knowing how to manipulate these kind of things properly allows you to get better in all these other domains of science or engineering. Okay, so it's not that for some years, for example, I assisted discussions on what is better, Euler angles, quaternions, or rotation matrices. Okay, so I will tell you this: a rotation and a matrix and a quaternion, they both belong to the Lie theory, and they are equivalent. For what we matter, they are equivalent. So it's the same. And then Euler angles have a lot of problems. They don't fit well in this theory. They have singularities and things like this, and they are not good. So the discussion can be broke down very quickly. And quaternions and rotation matrices are equivalent. If you like one or you don't know the other one, you don't need to learn the other one, because you don't, for the pleasure of learning is good, but you will have the same performance with quaternions, unit quaternions, of course, or rotation matrices. No difference. It's like in 2D, for example, if you want to work with complex numbers to rotate things, okay, you have sinus and cosinus of an angle here and there. If you want to work with rotation matrices, you have the same sinus and the same cosinus organized in a matrix. And you can do one thing or the other one, but the result is the same. So one is not better than the other one, okay? All right, let's see a subset of Lie groups that are useful in robotics. And for example, regular vectors are a particular case of Lie group, which is trivial. Okay, we will maybe discuss a little bit. This is trivial, not very interesting, but they also can be embedded inside the theory. Okay, no problem. Then the unit complex numbers, we discussed briefly about this. It's for rotation vectors in 2D. Okay, they have a number of theories. The elements are Z in the complex numbers. The constraint is Z conjugate Z equal 1. The elements of the Lie algebra, we will present what is this, okay, are imaginary numbers. The exponential map, wow, okay, we will also explain this today. Okay, it's like that. Composition is the product of complex numbers, and the action is the product of one unit complex number times a regular complex number that we interpret as a vector. Rotations in the plane, a special orthogonal group in 2 dimensions. Okay, same thing. Rigid motion, so rotations and translations, this kind of matrices, RT01, okay, good. In 3D, we can define the same operations. And for example, the unit quaternion, it's a vector of 4 components with a unit length. This defines a sphere of 3 dimensions. Okay, we are abstracting things as spheres of 3 dimensions. This is kind of the equivalent to the regular complex numbers. They work very much the same. Okay, Q conjugate times Q equal 1, and this kind of thing. No problem. Only there's a slight difference that the rotation is performed with this double product. To rotate X, you do QX, Q conjugate. Why not? This is the action. Rotation matrices in 3D, R transpose R equal I, no problem. Or rigid motion in 3D, this kind of matrices, same thing. Okay. All these groups are Lie groups, and they share a lot of properties. So if you understand these properties in an abstract form, immediately you understand all the groups. Okay, that's the power of this theory. In this table, I could have put more groups. For example, Sim2 and Sim3 are transformations in the style of a rigid transformation, but they allow for a scale change in the same time that you transform. This is very useful for doing monocular SLAM because the scale is not observed by the camera, so it can drift during the estimation. And maybe you want a group that allows this drift to be estimated later as one independent scalar. Okay, why not? And then when you want to deal with a little bit more complex systems, for example, if you work with IMUs that contain position and orientation, but also velocity, you need the velocity in the state to be able to work with IMUs. Well, you can define a new group, which is called SE2 in 3 dimensions. And this is very useful for doing motion integration for IMUs. Good, okay. And this is used in inertial SLAM, okay. So for example, a visual inertial SLAM, monocular plus IMU, could be working with these 2 groups together in some fancy combination, okay. Good. Okay, that was a long presentation. The course will be a little bit more detailed so that you can learn something useful and not only, waving hands as I've been doing up to now. So I did point 1 presentation with examples. Next, I will be presenting the Lie group, a formal definition, the group, the manifold, the action. We will talk about these 3 concepts. I will define the tangent space. It has 2 equivalent forms. One is a little bit weird and the other one is very easy. Okay, they are equivalent, so that's nice. I will present the exponential map. Maybe some of you have heard about this and thinks that it is a kind of an evil thing with magic inside. Well, it's actually quite simple to show what it is. Okay, the inverse of the exponential map is the logarithmic map, also very useful. Then I will present a couple of operators that I call plus and minus, that they are shortcuts englobing a number of operations in the groups. And you put this number of operations together and you define the operator plus and minus. And when you have plus and minus, they act as if it was the sum and the difference operators in vector spaces. We will see that this plus and minus, when we interpret them as sums and differences, allow us to reason in Lie groups the same way we reason in vector spaces. This is very powerful. I will introduce later the adjoint matrix, which is kind of an abstract object that is very useful later because, for example, it's used for derivatives. Okay, we will introduce derivatives, Jacobian matrices, these kind of things. Then we will talk about uncertainty, how to define uncertainty for elements such as a 3D rotation matrix. Okay, what is the uncertainty? How can I express an error in this rotation matrix? Okay, integration, how to integrate motion. For example, you have small velocities and you want to integrate them into a particular trajectory, integration. And we will end up with a couple of applications. And I hope we have time to do everything. I think so. So let's start. What is a group? A group is defined through 4 axioms. Okay, they are quite straightforward. A group is a set of elements that I will call G, of elements of the type X, Y, Z, together with an operation. Okay, that I will put here a little dot. Some people use other kinds of symbols. This operation is part of the group. Okay, the group is the set of elements together with the operation. So that, for example, if you operate 2 elements of the group with the operator, the result is in the group. Okay, that's why it's a group. The identity element is in the group. I call it E. If I operate any element with E, is the same as if I operate E with any element. And this gives the element unchanged. That's very nice. If you take a rotation matrix and multiply by the identity matrix, you get the same rotation matrix. Okay, that's the idea here. No surprise. There is an inverse for this kind of elements. Okay, I can define x minus 1 so that when I multiply by x, I obtain the identity in both directions. Okay, this looks quite logical, but not all sets with all operations satisfy this thing. So if you want a Lie group, it needs to satisfy this. It needs to have an identity which is inside the group. Okay, and the operation is associative. So if you group x, y, z by operating first on y, z and second on x, this is the same thing as operating x and y first and then z on the second step. Okay, good. These are the properties of groups. Okay, and very important, there is a non-property. There is something that you should not assume it is true, because it's not, is that this operator is non-commutative. Okay, so xy is different than yx. This is very important. If I give you the properties, maybe you extrapolate and you say, oh yeah, okay, it's not true. Okay, some groups are commutative. They are usually very simple groups. And very quickly, the groups that are interesting, for example, when you go to 3D, then the groups, the operation is very quickly non-commutative. Okay, in 3D, R1 times R2 is different from R2 times R1. You know this, okay? This is a group, okay? It's not yet a Lie group. This is a group. Let's see what is a Lie group. A Lie group is a group. Okay, so it's a set of elements with an operator satisfying the 4 axioms that is also a smooth manifold. Okay, what is a smooth manifold? What is a manifold, to start with? A manifold, you can see it as a kind of surface, okay, embedded, for example, this surface here would be a 2D surface embedded in a space of 3 dimensions, which is the ambient space where this surface belongs, okay? All the drawings that I will be doing are 2D drawings embedded in 3D, because I cannot draw in more dimensions. I cannot do it and nobody can do it, okay? So, but this manifold could be more than 2 dimensions or less. We have seen a manifold of 1 dimension. It was the unit circle. That was 1 dimension, okay? And smooth means that this manifold, this surface, has no edges or spikes. Okay, this is very important. Okay, so we don't consider this kind of manifolds. We consider the manifolds that are smooth. Of course, you can define smooth manifold through mathematical axioms and properties. I will not do that, because what I want to convey you is the intuition and the vision of what it is. Okay, so this is a smooth manifold. These guys here are not smooth because they have edges or spikes. They have certain places where the derivative is broken. Okay, right? So a Lie group is a group that is also a smooth manifold, or you can define it otherwise. A Lie group is a smooth manifold whose elements satisfy the group axioms. Same things, these 2 definitions have been prevailed in the history of this theory. So at the beginning, the definition was rather this one. A Lie group is a group that is also a manifold. And lately, I don't know why, people start to define it otherwise. A Lie group is a smooth manifold whose elements satisfy the group axioms. The same thing. Okay. So now we know what is a Lie group. Abstractly, we have the definition, and we can introduce what is the action of this group. So a group can act on another set V to transform its elements. Okay, we have seen this before in an example. So given X, Y elements in G, and V an element in the other set V, the action that I will draw with the same symbol as before, why not, is such that if you apply the identity of the group to the element is not changed. Of course, I mean, who would like to define things otherwise? Okay, and that the action is compatible, it's called compatibility, with the composition. So I can compose the group elements first and apply the action to V with the result of this composition, or I can apply first one action and then the other action, okay? And these two guys must be the same. If they are not the same, then this is not an action, okay? We need these properties to be able to construct nice results later on, okay? So Lie groups come with the power to transform other elements, and that's very nice, and we use it a lot, okay? We actually rotate things or translate things, okay? So the translation is an operation, and that's the Lie group part of the thing. And a rotation of something, this something is part of another set, okay? You rotate vectors with rotation matrices, okay? Fine. So we have the action, Lie group, and action. I hope you can follow this. It's quite simple. Up to here, just a few definitions, a few concepts. No big deal. Now I want to introduce for the first time what are all the elements that we need to know in Lie theory. And I call it the topology of Lie theory because you can actually draw them in space. All right? So let me replay this little animation once again. This would be a manifold defining the elements of the group. The elements of the group would be on the surface of this sphere, not inside the sphere, on the surface of the sphere, okay? And then I can define the identity element. I can put a tangent plane on this point. I can define vectors on this plane, and I would like you to recognize this 3D drawing because it's very powerful to understand what we're talking about, okay? So the manifold is this blue sphere. The identity element is a particular point in this blue sphere. So if this is the manifold of rotation matrices, okay, which are all living in this space, this point here is the identity matrix, okay? We can put a linear space, which is flat, tangent to this point. And if this point is the identity element, this tangent space is called the Lie algebra. Okay, we will talk about this later. This is called the Lie algebra. We can define vectors in the Lie algebra. This red line here is a vector, which is tangent to the sphere at the point identity, okay? This vector is tangent to this sphere at this point, all right? Then if you take this vector as, for example, a piece of string, and you roll it on over the surface, you end up in this point here, okay? Following this curve, right? It's like you wrap this line on the surface and you end up here, okay? So you can make an equivalence from this point here belonging to the tangent space to this point here belonging to the group. That's very nice because groups are non-linear things, weird, and the tangent space is a vector space, very easy to work with, okay? So it's nice to have a exact equivalence between these two guys, okay? And this equivalence is called the exponential map, okay? We will talk about the exponential map later, but this operation of rolling a tangent vector onto the surface until we reach a point in the group, this is the exponential map, Why is it called exponential? We will see it later. Okay, it's maybe a little bit surprising, but yes. And of course, the opposite is the logarithm map. All right. So all the important things that I will be talking about today are in this drawing. So make a, a visual picture of this, because I will be going around this thing for a while in different directions. Okay, that's a very important drawing. Let's see. Let's talk first about the tangent space. So we have a smooth manifold M, whatever the shape is, it's not flat. And we have a point X belonging to M. And in this point, because M is smooth, there is a unique tangent space. That's the importance of smoothness, is that at any point, you can only put one tangent space. Okay. And this tangent space, we noted TXM is the tangent of at the point X of M. Okay, tangent at X of M. Right? We note it like this very usually. So properties of the tangent space: the tangent space is unique. The tangent space is a vector space, so it's linear space, and therefore we can apply all the calculus, derivatives, integrals, and these kind of things because it's a vector space. The dimension of the tangent space is the same as the number of degrees of freedom of the manifold. So in this manifold, you could move in two different directions. For any point, you have a 2D surface. Okay, so the dimension of the tangent space is 2D in this case of the drawing. Okay, and as I said, the tangent space at the identity is called the Lie algebra. Okay, so far for the tangent space and the Lie algebra. If the tangent space is at the point X, which is not the identity, then we don't call this tangent space the Lie algebra. It's a tangent space anyway. Let's see what is the. Let's do a little bit of algebra. Put some symbols and operations to this otherwise very abstract discussion. Okay, we have the manifold of unit complex numbers. All right, and we have a point moving on this manifold. Okay, because it's moving on this manifold, it has a velocity, and the velocity is tangent to the curve. You know this, okay? The velocity is tangent to the trajectory. This is well known. So the velocity of z prime or z dot belongs to the tangent space of the manifold. Okay, right? And if the tangent space is the identity, okay, this tangent line is vertical. And so the elements of this tangent at the identity are pure imaginary numbers. This vector has no real component. It has only imaginary components. This vector has real and imaginary components. Okay? So far, let's see how can we discover a little bit how to relate z dot, and I omega in some equation. Okay? Because these three guys must be related somehow. Okay? So let's take the constraint defining this group, z conjugate times z equal 1, and let's apply the derivative with respect to time. So we get z conjugate dot z plus z conjugate z dot equals 0. This is the derivative of this constraint. Okay, we manipulate a little bit, and we arrive at the following expression. This is very important. Z conjugate z dot equals minus z conjugate z dot conjugate. This is a manipulation of this equation here. No big deal. You put this on the other side and put the conjugate outside and manipulate a little bit. You get here. And now the important thing is to realize that what is inside this parenthesis, okay, z conjugate z dot, is the same as what is here. So this element z conjugate z dot, it's equal to minus its own conjugate. Okay, and in the complex plane, the only elements belonging to the complex plane that are equal to minus their own conjugates are pure imaginary numbers. Okay, the conjugate of I omega is minus I omega. It's minus, the element is equal to the minus its own conjugate. So now we know that Z conjugate Z dot is always a number of this form, I omega with omega in the real numbers. Okay. So we write the constraint, we differentiate, we manipulate a little bit, and then we discover what is the shape of this element so that this equation is satisfied. And it means that this element is imaginary, and then we can write this equation here. Okay, so now we related Z with Z dot and with I omega, which is the elements appearing in this drawing. Okay, the Lie algebra is the space tangent to the identity. So it's formed by the elements of the type I omega. Okay, we saw this already in the drawing, but now we can see it here. If Z equals 1, then we have Z dot equals I omega, and that means that the tangent is the imaginary axis. Okay, so I omega belongs to IR, it's an imaginary number. And the elements of the Lie algebra, we note them, myself and many other people, with a hat operator, this kind of operator, telling you that this element belongs to the Lie algebra. Okay. In contrast, the bare element omega, it's just a number, a real number. Okay. So we can see that if we want to parameterize this space, which is a linear space, we can either use elements of the type I omega, or I can just tell you omega. And because you know it's an imaginary number, but you multiply by I. If I give you omega, you have the same information as if I give you I omega. It's one line, 1 degree of freedom. I just need to tell you what is the height of the point you want to consider, and the height is omega. Okay, so the tangent space can be defined or represented in two equivalent forms. One is the Lie algebra, which is usually a little bit weird. Okay, in this case, it's imaginary, but in other groups, you will find other kinds of constructions. Okay, but because it's a linear space, you can always, you define the base, and then you define the coordinates of any vector expressed in this base, and you put these coordinates in the form of a vector. And so you always have a Cartesian representation of points in the Lie algebra. Okay, we will see it later. It's nice. So because they are equivalent, we can go from Lie algebra to Cartesian, or from Cartesian to Lie algebra with a couple of linear operators that we usually call hat and b. Okay. Let's see an example. Rotation matrices in 3D. Okay. This is a surface that I draw in 2D. This is a regular sphere. So the surface is 2D, but this is a representation of the real surface of the group of rotation matrices, which is a 3D surface. Okay, I cannot draw a 3D surface. Okay, but I draw a 2D surface. At least you see a surface. One point in particular in this surface is the identity matrix in 3D. It is this point I. Okay, if you move, you start rotating and you depart from the identity with a certain velocity. This velocity is omega cross. We will talk about this also. After a certain time, you are here at the matrix R. Okay, and this vector here is R dot, which is tangent to the manifold. Remember that the same thing we saw here, but in 3D. Okay, it is the same idea, but in 3D. All right, let's see on the right part, algebraically, how can we advance and see what kind of objects are the elements of the Lie algebra and these kind of things. So we take R transpose R equal I, we differentiate with respect to time, and we get R transpose dot R plus R transpose R dot equals 0. We rearrange this and we get this thing. And you see that what's inside the parentheses is R transpose R dot is the same as here. So you need to find what elements satisfy the following property. These elements must be equal to minus their own transposes. What elements are minus their own transposes? they are all skew-symmetric matrices. If you want to satisfy this, you need a matrix R transpose R dot, which has this form. You cannot escape from this form. Okay, this is equal to minus their own transpose. And because of this, you have 3 degrees of freedom. You have 3 zeros here, and every element out of the diagonal is related to the other one with a minus. So you have 3 degrees of freedom for the Lie algebra. Okay, and so you could place a tangent space, tangent here to the identity. It would be a 3-dimensional space. Okay, and it's the space of skew-symmetric matrices. Okay, of course, R is the identity. The tangent space R dot is exactly this skew-symmetric matrix, which we represent by omega cross. Okay, this cross comes from the cross product and so on, but we indicate with this cross a skew-symmetric matrix. Let's dig a little bit more into this example. So we have skew-symmetric matrices. This is the form of the elements of the Lie algebra, and we write them as a linear combination of 3 base matrices: omega x, omega y, omega z. You can find them here, up here, and they can multiply by 3 constant matrices, which is the base of this. And now we take these 3 elements and we construct a regular Cartesian vector with 3 elements, okay, which satisfies, of course, this other equation. It's easy to see that this thing here is absolutely equivalent to this one here. If I give you this vector, you can construct this matrix immediately. And if I give you this matrix, you can construct this vector immediately. All right? These 2 spaces are the same space, and it's the tangent space at the identity, so the Lie algebra. It's the same space, but it's represented by different objects. Okay, these are matrices. These are vectors. To start with, the objects don't even have the same form, the same container, let's say. Okay, and you have an isomorphism. You can build matrices from tangent. You can build tangent vectors from matrices, or matrices from vectors going from here to here anytime you want. Okay, this transformation from Lie algebra to Cartesian is just a linear transformation, usually quite trivial. All right. So we spoke about the manifold, the group, the tangent space, and the Lie algebra, and what kind of mathematical form have these elements of the Lie algebra, and so on. Let's now introduce the exponential map. As I said before, the exponential map allows you to map elements of the Lie algebra, a point here on the plane, into elements of the group by rolling this vector over the surface. Okay, we explained this before. Now we're going to see how this works. Exponential map goes from tangent to manifold, wrapping on the geodesic. The geodesic is this curve here. And the logarithmic maps goes the other way around, the opposite way, from the manifold to the tangent space. I would like you to realize, or to see this small, slow animation. You have a point that starts at the identity and has this velocity, okay? But of course it has this velocity, which is tangent. The tangent escapes the manifold, but the point is not allowed to escape the manifold. So this is how things will work, okay? You have a point that is rotating on this manifold. It's going this way. And a tangent vector that, if you integrate it, goes this way. Okay. Our idea here is that you can go from here to here, because these 2 points must be equivalent in some way. We must have a map that goes from here to there and back. This would be the exponential and the logarithmic maps. So we need to, again, on the right-hand side, work equations and see how can we find a form of this map, a mathematical equation or something that allows me to take theta, which is a number, and produce z, which is a complex number. I don't know. Let's see. So we take this expression that we saw before, z conjugate z dot equals I omega, okay? We put z conjugate on the other side, and we get this. Z prime equals zi omega. This is an ordinary differential equation. Z dot equals zi omega. And you can integrate this equation very easily. So z of t is z0 exponential of I omega t. This is the solution, general solution of this differential equation. For those who find this very, very surprising, you just need to differentiate this with respect to time. You will find z dot equals, this is a constant, z0. This is the exponential. So the derivative is the same exponential times the derivative of what's inside, I omega. And so z0 exponential of I omega t was z. So this gives you zi omega, which is what we wanted. Okay? So this is the integral or the solution to this differential equation. And this differential equation came from differentiating the constraint with respect to time. This is what we did 2 slides ago. Okay? So we have this equation. Now, imagine that we say, okay, we start at z0 equal 1. We start here at this point. Okay? And we define omega t equal theta. Omega is an angular velocity because we are turning, and omega t will be a certain angle. We call it theta so that I have to write a little bit less. Okay? Let's see, z of t now is the exponential of I omega t, or what is the same is the exponential of I theta, according to this expression. Okay? So now it's very easy. We apply the Taylor expansion of the exponential, and we know that my elements, as I will not exponentiate, but I will raise them to different powers, have some properties. For example, I to the power 0 is 1. I to the power 2 is -1, you know this. And I to the power 3 is -i. Okay? So, exponential of I theta is the Taylor series, is 1 plus I theta plus I theta squared divided 2 plus I theta cubed divided 3 factorial, and this goes to infinity. Okay, no surprise. Let's manipulate a little bit this expression. We know that I squared is -1, so we put a minus here. Good. We know that I cubed is -i, so we put -i here, and we keep going. Okay, this goes to infinity. No big deal up to this point. Now, in this series here, we realize that every 2 elements, we have a real number. So 1 minus theta squared divided 2, theta 4 divided 4. I think I should have removed an I here. This is not here. And every other element, every other element is a pure imaginary number. Okay? So I can group reals and imaginaries like this. All the reals go here, all the imaginaries goes here. And now this parenthesis is exactly cosinus theta, and this parenthesis is sinus theta. So the result is cosinus theta plus I sinus theta, which is like, okay, cool, because I already knew that a unit complex number can be expressed as the cosinus of the angle plus I sinus of the angle. This we know, but this method allows you to get here, and this method you can replicate for any other group that you like. You can now go and see the rigid motions in 3D. You apply the same method, and you will find what is the closed form of the exponential map for tangents vectors of the translation and rotation operations in 3D. And that's not trivial, okay? And so this method is useful for all the groups, and that's the nice part of it, okay? I want to focus for a minute over this line here, okay? I will, well, okay, let's go. Well, this is the exponential map. This is the logarithmic map. We will insist on this a little bit more. Let's focus on this line here, okay? And excuse me for this, try to remove this I from your brain. So I theta to the power of 4 is theta to the power of 4, because I to the power of 4 is 1, okay? let's see this sum here, which goes to infinity, and let's work it out element by element, okay? So we start with nothing, and we add 1 to nothing, and we go from 0 to 1. Now we add the second element. This is plus I theta. I is imaginary, and plus it means we will go up in the direction of I, okay? And we will go up an amount theta. So we will go exactly here, okay? Now, third term is minus, it's real. It's a real number, and it's minus. So we will go to the left now, okay? And the next one is minus I, so we will go down, okay? And there is a factorial which will make these numbers progressively smaller, actually at a quite fast. They get small very fast, okay? So we went down this way. We add the fourth one. This is a real number. We go to the right, okay? And when we add all of them, we end up exactly at this point, okay? So this is the exponential map. You can see it doing some calculus, okay? I can convince you that this is true. You can see it with this geometrical interpretation of wrapping a string over a surface, same idea, okay? Or you can see it by the sum of elements of the exponential. There are 3 ways to see that the exponential of this goes here, okay? Very nice. So we got z from theta, or from omega delta t. Okay, that's the exponential map. Very important, it's central in this theory. And I think you have all the elements. You have a method to devise the exponential map for any group that you want. You have closed form for many of the groups. You have a nice interpretation in terms of geometry that you can imagine in your head, okay? And just as a proof that this can be done in other groups, let's do it for the rotation matrices, okay? Exactly the same thing. We take R transpose R dot equal omega cross, which is a skew-symmetric matrix. This is the form of a skew-symmetric matrix in 2D. We have this differential equation. We integrate, we get this. Same thing, R of t is R0 times exponential of omega cross t. Up to here, no problem. Now, if R0 is the identity, it means we will start here. And omega cross t, we call it theta cross. Okay, so omega t is theta. Okay, and we get this expression: R of t is the exponential of theta cross. Okay, and now we need to know that these elements, if you put 1 cross, which would be 0 minus 1, 1, 0, to the power of 0 is I, of course, and to the power of 3 is minus this element. It behaves the same as the imaginary number. The third power is minus the element. Okay. You apply the Taylor expansion, I plus theta 1 cross. Remember, theta cross is theta 1 cross, plus theta 1 cross squared divided 2, plus theta 1 cross cubed divided 3 factorial to infinity. Then you group the elements depending on I here, and the elements depending on 1 cross here. Okay, and now this is the cosinus of theta, this is the sinus of theta, and you get this sum, I cosinus theta plus 1 cross sinus theta. And then you arrange, this is a matrix, this is another matrix, you put them together and you get this matrix. Good. You knew that this was the rotation matrix in 2D, but
excuse me, Joan.
Same method. Yes.
Yes, you have a question.
Okay.
Can you see it in the chat?
I have to minimize. Go to the
Google Meet and click.
The question is,
yes.
Can this still be useful if there is no closed form solution on the constraints? Wow, that I never had this question before. Peter Disnikar, thank you for this question. If you don't have a closed form, yes, you can still apply Okay, I read the question. Let me go back to the, how should I go back now? Okay, here. Can you see the screen now? Yes, no? I will give you the answer now. Hello?
Yes, you see it.
Can you hear me? I have no reply. Can you hear me?
Yes.
Okay, okay. So if you don't have a closed form for any reason, you can always resort to the Taylor expansion, and knowing that the factorial will get big very quickly, these numbers will get small. So you can truncate this series somewhere. Okay, truncating at the linear term is, at the constant term is not nice. Linear term, sometimes we do it. We have this approximation of the rotation matrix, or you can truncate a little bit later. So if you don't have a closed form, you have a way to find a rotation matrix which is close enough to the true value. But then you are approximating. Okay, it has some risks there. But yes, the answer would be yes, but with this little caveat. Okay. I will go on. If you have more questions, please don't hesitate. And Victor, please, if you interrupt me, because I don't see during the presentation, I don't see the questions.
I've got a question. How do you convert the last expression to the matrix?
Oh, because I is the identity matrix. So you have cosinus 0, 0 cosinus. Okay. Yes. And then 1 cross is this matrix with 1 minus 1 here and 1 here. You multiply by sinus. So you have 0 minus sinus, sinus 0. And then you sum these guys together and you get here. No big deal. Huh?
Oh, okay, okay.
Okay. Yeah, it's very simple. Okay.
Yes, thank you.
Okay. Let's keep going. Realize now that we are dealing with these kind of objects. Okay. In one case, it was an imaginary number. Now it's a skew-symmetric matrix of dimension 2. Some time ago, we saw the skew-symmetric matrices of dimension 3. These elements are all in some way strange, okay? And they do not generalize easily, okay? So now let's introduce what I call, and some other colleagues call it like this, but this is not part of the theory if you want. This is a first cool shortcut, okay? Let's call R, let's go to this left drawing. This is what we just saw, R equal exponential of theta cross. Theta cross is a skew-symmetric matrix. R is a rotation matrix, okay? Theta cross has 1 degree of freedom, which is theta, okay? So let's say R is the exponential of theta. Why not? And we call it this big exponential to differentiate from the small exponential. You can see this is a shortcut. So from this definition, you take theta, you construct the skew-symmetric matrix by adding this operator cross. Okay, you construct the matrix, and then you do the exponential. It's like a two-step function, and this is a shortcut. It makes the same thing in one go. Okay. Okay. And the exponential, of course, is this little matrix, cosinus minus sinus, sinus cosinus. All right. This is the same as saying that we have an isomorphism between the elements of the Lie algebra, which are weird, and the elements of the Cartesian representation of the Lie algebra, which are very nice, just one number here. Okay. This can be summarized in this little sketch. So you have the manifold, which is nonlinear, curved, and so on. And you have the tangent space, which is flat, linear, and so on. Okay. And you have two representations for the tangent space. Let's call all vectors in the tangent space expressed as Cartesian vectors. Let's call them tau. Why not? Tau, it's just a letter it shows. It's a Greek letter, and it's tau because it's tangent. Okay, why not? It belongs to Rm. This is a linear space of dimension m. whatever n, okay? Then I can apply the hat operator, which is a linear operator, to produce tau hat. Tau hat is these weird elements of the Lie algebra. Okay, for example, tau could be a 3D vector, and tau hat would be a 3x3 skew symmetric matrix. Okay, that it's constructed from these three components, trivially. Okay, now from here to the manifold, you have the exponential. Okay, so the big exponential is just the combination of the two operations. So nothing else to say here. And the big log map is the combination of the two arrows on the other direction. Okay. Nothing else than this. It's useful because now we will stay in this representation, usually. Okay. Because these guys are vectors. Very nice. These guys are weird. These guys are vectors. So we want to go from here to there in one go. And this is why we define these two shortcuts. Good. Next shortcut, it's the plus and minus operators. So remember that in the group, this is any group. I just make circles because why not? It's easy to draw. The concepts are visible. But I'm not meaning here that this only applies to the unit circle. This is any manifold of any dimension. Okay, no problem here. We have the identity matrix. We have two elements, x1 and x2, and we can compose them producing an element x1, x2, which is part of the manifold because this is a group. Okay, this is one kind of operations that we have from the group, and then we have the exponential map. Any element of the group can be expressed as the exponential of some vector in the tangent space. Okay, this is what we just saw, and we will combine these two things together as follows. So we have an element x. At the tangent space of x, we put a vector w, or omega, actually. We put a vector omega. We do the exponential of omega and compose it with x. This point here is x times the exponential of omega. I hope you agree with me. This from x to here is the exponential of omega, this part. And this part from 1 to x is x. So x times exponential of omega brings you here. Okay, this is this point here. And now to this operation, we define an operator which is called plus, and we call it x plus omega. This is just a definition of some things that we already have defined, and we again produce a shortcut that is called plus. Why we do this? Because look what we did here. We had a vector, group element. For example, we had, let me put this example. We had a 3D rotation matrix. Okay, and then we had an error of this rotation matrix. You know that rotation matrices have 3 degrees of freedom. So if I have an error or an increment or some update step on this rotation matrix, depends on you if you are doing control or you are doing estimation or whatever, you have elements and you want to modify them a little bit because there is an error, there is a correction of a Kalman filter, there is a control law that tries to modify certain things, okay? So you have 3 degrees of freedom, so you want to express this error with 3 numbers. Remember, a rotation matrix in 3D has 9 numbers. You don't want 9 numbers freely, because then these 9 numbers maybe they are not a rotation matrix. So you have 3 numbers, so you put them in a vector, and you just add in quotes this vector to the rotation matrix. And the result, because of these definitions, the result is a valid rotation matrix, which is somewhere else. Okay. Very usually, this omega, it's a small value. So this drawing should be like x and x prime a little bit close here. But the result is part of the manifold. So if you apply this operation, x plus omega, the result is strictly a rotation matrix, and it satisfies all the properties of rotation matrices because we defined it properly. Okay, remember I said this is a proper theory the things that we do are proper. They are well done and they are exact. This operation here, it looks like a sum, but it's not. But it looks like, and it's not an approximation of something that we force it to look like a sum by compromising some exactness. We didn't do that, okay? This is exact, but it looks like a sum. And so we will be able to sum or subtract things, and these things will be vectors. This is very nice when you want to do derivatives or covariances matrix or errors or this kind of things. Okay, that's the plus operator. Of course, we can define the minus operator. Imagine you have two rotation matrices, y and x, that are, for example, y is, or let's say x is a rotation matrix, and y is another one that is your estimate of the proper rotation matrix. Or you have two versions of it, and you want to know what's the difference between them. Okay, there is a small error. You want to express this error as a 3D vector, because there are only 3 degrees of freedom. So you do y minus x, and it's actually composing y minus 1, x minus 1 times y, which is this fraction here, and then do the logarithm and go to the tangent space. Okay, so you do the logarithm of x minus 1 times y, and you get y minus x. These two operations are, one is the reverse of the other one. Here you have a group element, and you can add some increment in the form of a vector to get another group element. Here you have two group elements, and you want to find the difference between them, and you want to express this difference in the form of a vector. Okay, again, this is proper, and you can do this operation as many times as you want. This is no approximation, this is proper. Okay, all right. Now, let's, using this plus operator, let me introduce a concept that looks like a bit disconnected from everything else, because it has a less intuitive entity. So I will not explain it in the same way, but it's an object that is very, very interesting. Okay, imagine that you have a manifold, M, whatever, and you have the identity element, E. Okay, you have a point X, and of course, E times X is equal to X. So you go from E to X by multiplying by X. You get it here. And you can add tau over X by putting the tau as a tangent to X and doing the exponential. And then you get to the point Y. Okay? And then you can ask yourself, oh, I could have done things differently. Like, let's get a vector here. Let's do the exponential. And then let's multiply by X on the right. Remember that the composition in the group is non-commutative. So this way, X times exponential of tau is different from this way, exponential of sigma times X. Okay? So you can express this Y element into forms, either sigma plus X or X plus tau. And if you manipulate a little bit these expressions following the definitions, you arrive at this form. If you stay in the Lie algebra form of sigma and tau, you see the hat here, this is the Lie algebra form. But if you express sigma and tau as vectors, because this is a linear form, this is linear. So if sigma and tau are vectors, this linear relation can be written as a matrix. Okay? And so this matrix is the adjoint matrix. It's an operator that is linear, and it maps elements tangent to M at the point X. So this element tau is tangent to M at the point X, and it maps it to tangents at the identity, sigma, so that you can compose on the left or on the right and get the same result. Because the composition is not commutative, sigma and tau are different. Okay. If by any chance you are in a group where composition is commutative, then of course sigma and tau will be the same, because it doesn't matter if you put it on the left and on the right. If you want to get the same result, then they must be the same. Okay, the adjoint matrix. I will stop here for the adjoint. Sorry to not provide more intuition, but this is a quick presentation that is enough. We will use the adjoint a little bit later, so it's good that you know what it is. It is a matrix that relates tangent vectors at one point to tangent vectors at the identity. Okay, this drawing, because we are in a Lie group, everything here is connected some way. Okay, x is equal to x, of course. And what's the relation between tau and sigma? Well, this is the relation between tau and sigma. Okay. Let's start doing calculus. Calculus means doing differentials, differentiation and integration, and therefore dealing with uncertainty and these kind of things. We will use for this the plus and minus operators that we defined. Okay, and as follows. Yeah, as follows. The derivative in vector spaces, is defined as this. You perturb the point, then you apply the function to the point, you subtract the function, you divide by the perturbation, and you get this derivative, which is a matrix if you are in a vector space. In the groups, we will do exactly the same. We will use the same formula. I will change the partial symbol here by a capital D, just to note that it's not exactly the same. And I will put, instead of plus, I will put this O plus. And instead of the difference here, I will put the minus here. So what happens now is that tau is a regular vector, okay, that I can add to x. Then f of x is a member of a manifold, whatever. X is a member of a manifold. F of x is a member maybe of another manifold. F is any function. Then f of x is a member of a manifold. F of x plus tau also a member of this same manifold. I do minus. This minus gives me another vector. And so this limit, when this vector divided by the other vector, this is a Jacobian matrix. It's a matrix, the same. Okay. How do we proceed to compute this in vector spaces, to compute these matrices? Remember that this formula is a bit strange because we are dividing by a vector. This is not well defined, but it's a nice notation. What we do is manipulate the numerator. It's easy to manipulate because we are doing the limit when h goes to 0. So it's we can apply a lot of simplifications until we get to a form like this. And once you get the linear form in the numerator, well, this is exactly the Jacobian, the derivative of this, and that's the Jacobian. And here we will do the same. You write this formula, and you apply a limit, and you apply the definitions of minus, which is the log of blah, 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 and plus, which is the exponential of tau. You apply this, and you start simplifying things, knowing that you have this limit. Okay, you can simplify many things. And you end up having this kind of form, and now you have J. Okay, this is the way to proceed. Let's see one example. Imagine you have a function from SO3 and R3 to R3. This is a function that takes a rotation matrix and a certain vector and rotates this vector. Okay, this function has 2 arguments and it produces 1 output. Okay, let's find the derivative of RP with respect to R. Okay, and this is the Lie derivative. Attention, because if you want to differentiate with respect to R, and R is a matrix, and you are stuck with your vector space definition, then this is not work. This doesn't work. So you apply the definition. R plus theta is R exponential of theta, because here inside the parentheses, we are in R3, in SO3, excuse me. But the minus here, it's a regular minus because that's the result of the function, and this is a vector. So we apply a minus here. And so you keep going. Now the exponential, you can take the Taylor expansion and truncate at the second term. And this is not an approximation because we are doing the limit. So this is true in the limit. Okay, it's not an approximation. It's true in the limit. We did this. Now you can simplify this RP with this RIP, and you get this. Okay, and now the properties of the skew-symmetric matrix is that theta x times p is equal to minus px times theta. So you write this, and now you have it. You have the linear form multiplying theta and dividing theta. So this Jacobian is minus r p cross. Cool. And this is a 3×3 rotation matrix, 3×3 Jacobian matrix. Okay, it's a little bit long, but you can do it. But just applying definitions. The second, oh, wait a second. Yeah, this I already said. This operates on SO3 because it's the argument of the function here. So this was a rotation matrix. So you need to apply plus. However, this operates on R3 because it's the output of F. And the output of F, in this case, it's a vector. So here you can put a regular minus, which works for vectors. The other derivative is very simple because now you will perturbate a vector. So you perturbate with a regular plus, and this simplifies very quickly. RP minus RP goes away. You have this, and this Jacobian is R very quickly. Okay. The Jacobian can be interpreted graphically. So you had a function that goes from one manifold to another manifold, and you have a tangent space here. You perturbate, you apply plus. We are following the numerator. You apply F, you apply minus, and you get this perturbed vector. And then you do the limit when tau goes to 0. Do this limit, and then this tangent line is one of the columns of your Jacobian matrix. I will skip this part. Some intuitions graphically. So differentiation rules. So for each group, we can compute the adjoint, the Jacobian of the exponential function, or the Jacobians of the action. Okay, this we can find closed forms for every group. Then we have a nice set of nice properties for all groups. For example, the Jacobian of the inverse is always minus the adjoint, and this happens for all groups. And we have a number of properties that belong to all groups. These guys have to be computed for each group. These guys belong to all groups. And then other formulas can be derived from the previous ones. So the Jacobian of the log can be derived from these blocks here. Okay. So for all groups, you can find a lot of formulas for the elementary, the Jacobians of the elementary operations. And then when you have a complicated formula, like the differential of R transpose P with respect to R, you apply the chain rule. And you apply the chain rule, and you get here. Okay. So computing Jacobians for operations involving elements of Lie groups is doable, it's rigorous, it's nice, and you get Jacobian matrices the same way that you got Jacobian matrices in vector spaces. Next thing to do is perturbations. So you have a manifold, you have an element of this manifold, for example, X bar, and you want to perturb this element. When you perturb X bar in the manifold, you will go around the manifold. You can see the blue shape. It would be like the probability region of these perturbations. But we will express the perturbations not in the blue space, but in the red space, which is the tangent. Okay, so we will perturb X bar with vectors tau, obtaining new points, X equal X bar plus tau. Okay, or if we have 2 points, X and X bar, we can find the difference with minus. And this is a vector tau in the tangent space. The covariance of X, we will define it through the covariance of tau, because this is a vector. So we apply the definition of covariance for tau, and we substitute tau by X minus X bar, and this is the covariance of X. Okay, and if I use this fancy operators, is because if X were a member of a vector space, this would be a regular minus, and this is the typical definition for a covariance matrix. Okay, and then if you want to propagate this covariance through a nonlinear function, for example, You have y equals f of x. So y will bring this point to somewhere else in another manifold. You have y, and you want to propagate this uncertainty to the other manifold. Very simple. You compute the Jacobians as we just saw of this function, and you multiply left and right as we usually do in vector spaces. So now we can see that once we have introduced all these elements of the B theory and all these shortcuts, now we can reason the same way we have reasoned all the time in vector spaces. So for example, if you are used to do Kalman filtering or nonlinear optimization or different control laws on these kind of things, you can reason the same way, but now with the rigor and property of the theory. Integration is the last element that I want to discuss. We have seen that if you have a point and you have a constant velocity in the tangent space, you can integrate this trajectory with the exponential map. We saw this before. And if the velocity is not constant, you just need to break it into piecewise constant bits, okay? And now you have that this x4 is x0 plus omega 1 dt plus omega 2 dt plus omega 3 dt. And each time you do plus, you do this exponential, this exponential, this exponential. And you can integrate, for example, omega can be a measurement of velocity of your vehicle, and x is the pose of your vehicle. So you can produce a trajectory of poses by just integrating tangent vectors. Okay. I'm a bit short of time, I guess. I think so. Let's do one example, okay? A Kalman filter, and I will not do the other example, which is nonlinear optimization, but the concepts in the Kalman filter are here. We will do map-based localization based on a Kalman filter. In this problem, it's a problem on the plane, and the states of the vector, you can see for the robot, you can see the robot has a trajectory, x1, x2, x3. The poses of this robot are represented by elements of SE. Oh, actually, this is 3D, so SE3, okay? And the covariance is defined like this through the minus operator. So you have, for a Kalman filter, the elements you want to estimate and the covariances, as usual. And we consider a number of landmarks or beacons, okay? In this case, we will consider them known. So we are not doing SLAM, we are doing just map-based localization. And these BK are points in 3D, okay? Now, we introduce the motion model. So xi is a function of xi minus 1 and ui. U is the comment or the control law that you apply to your vehicle. So it's actually a velocity times time, okay? So you can say that the next state is the old state plus the velocity times time plus a certain noise, okay? And this noise is a Gaussian, right? Kalman filter and the measurement model. You can express the measurements of a beacon from a robot. If you want to express this in the reference frame of the robot, you have to do a frame transformation from world to robot frame. And this is the action of SE3. SE3 is transforming points from one frame to the other. So x minus 1, BK, plus noise. Okay, this is your measurement model. And the noise is, again, a covariance matrix. Now you have all this. And we construct the Kalman filter. Prediction, x hat becomes x hat plus ui dt without the noise because we are doing prediction. And we compute the two Jacobians of this function. The Jacobian with respect to x, we call it f, and the Jacobian with respect to omega, which is, this omega, yeah, it's actually, this is u, not omega. The Jacobian with respect to this part, okay, we call it g. And now we apply the formula of the Kalman filter because these Jacobians relate tangent spaces. And so I can map the covariance at the time I to the covariance at the time I plus 1 by just mapping the covariance as we saw. So this is the same formula you use for prediction of the covariance in a regular Kalman filter. Correction, you compute the innovation. In this case, it's like this. Okay, it's the measurement model. Because the result is a vector, you apply here regular minus. This is your measurement. And you compute the Jacobian of this function with respect to x in the same way that we computed Jacobians some minutes ago. Once you've done this, you apply regular Kalman filter operations, except for the update, where, because all the Jacobians and perturbations are in tangent spaces, the Kalman gain will relate measurements to the tangent space of the state. So the update step is applied with a plus to the real state. Okay, so that's the update operation, and that's the update for the covariance matrix, which follows the same formula. If you don't know Kalman filters, this last slide is maybe a bit mysterious for you, but if you know Kalman filter, you should be able to recognize the regular operations with some key differences. The first key difference is that the covariance is defined through the minus operator. Another difference is that we use plus to integrate velocity into motion of a state, which is not a vector. It's an element of a Lie group. Okay, we use plus. This is tangent velocity. Another concept is, for example, if we use the inverse of the element of the group, we'll use the action. Okay, all the concepts that we are introducing in Lie theory. We use Jacobians computed according to the formulas that I provided some minutes ago. It's the Lie derivative. Okay, it's not a normal derivative.
Excuse me, Joan.
Yes.
Just to let you know that we are out of time.
Yes, I'm done actually. Okay.
Okay, thank you.
Yeah, just the last slide. I'm sorry, but yeah. So that's the last note to give, is that the update is also using plus. This other example is similar, nonlinear optimization, same thing. And just before finishing, I would like to give you a few pointers. So a paper that we wrote in 2018 explaining everything that I explained here, a C++ library, which is quite powerful, implementing all this, just a sheet of a lot of formulas, and some courses on YouTube that I have covering the same topics. I will try to provide these links to the material of the school later on. And that's it. Thank you very much. That was it. Thank you.
Thank you very much, Joan.
Let me see if I can go back here. I don't know. Maybe we don't have time for questions. I will, Victor. You can provide my email to all the attendees.
Okay.
You feel free to write me or whatever with questions. Okay.
Yes.
Thanks to you all. See you around. Good luck with your projects.
Thank you very much, Joan.
Bye-bye.
Bye.
Thank you, Victor.